let's say we have this object of unknown mass, and to begin with, it's already in motion. Let's say it's moving to the east. Assume this is a top-down view, so we don't have to worry about gravity. So we've just got north, south, west, east. Let's say to begin with, this is moving to the east at some initial speed. Let's say the initial equals 5 meters per second. And let's say we find that this object, or we observe this object to explode into 3 pieces. Let's say one object with mass m, and other objects with masses, let's say twice as much and 5 times as much. So mass m, mass 2m, and mass 5m. So it explodes into these 3 pieces, and those 3 pieces end up scattering in different directions. Let's say the 5m piece comes to a complete stop. And let's say the 2m piece ends up traveling directly to the southeast, so at a 45-degree angle at speed, let's say 20 meters per second. So that's, let's say that's exactly a 45-degree angle directly southwest, or sorry, southeast. And let's say we don't know anything at all about the other one. We want to figure out where does this other mass end up, or which direction does this other mass end up going and how fast? So with that information, if we don't even know the masses, just the ratio of masses, they split into a piece, another piece twice as big, and another piece 5 times as big. We know the 5 times as big piece comes to a complete stop during the explosion. The 2 times as much piece ends up traveling at 20 meters per second. And the other one, the small mass, we don't know where it's going. Actually, let me call those capital M so we don't get it mixed up with the meters. So what could we do here? How could we figure out which direction and how fast the small piece is going at the end? What would be a technique we could use?
Would you have to break up the 20 meters per second at 45 degree into horizontal and vertical components?
Yeah, in general, anytime you're dealing with a 2- or 3-dimensional situation that involves vectors, I would recommend, before you even do anything else, it's often a good idea to split up all the vectors into components. So that 20 meters per second, if we wanted to split that into horizontal and vertical components, how would we do that?
Cosine and sine.
Sorry, go ahead.
Cosine and sine.
Yeah, we could use cosine and sine. And since it's a 45-degree angle, what do you know about cosine of 45 degrees and sine of 45 degrees?
Oh, it's 45, 45, 90.
Right, those are the same angle. So this is an isosceles triangle. What does that tell you about these 2 legs?
Root 2 over 2.
Sorry, what was that?
It would be the magnitude times root 2 over 2.
Right, they're both going to be magnitude times root 2 over 2. So they have the same x component and y component other than directions. So we can say each of those, and you can always write this as cosine of the angle equals opposite over hypotenuse. So in this case, that would be Vx over, or I guess Vy would be, sorry, cosine is adjacent. So Vx over 20, since the adjacent side is x component. And then Vx will be cosine 45 degrees times 20 meters per second. Cosine 45 is root 2 over 2. So we're going to end up with 10 root 2 meters per second. So that'll be the x component. And the y component is going to be the same, although since it's to the south, we'll probably want to call that negative. Also, let me label these objects. Let's call these objects object A, object B, and object C. So we can refer to them more easily than the 5 times as big piece and the 2 times as big piece. So object B has a final velocity of 10 root 2 to the east and 10 root 2 to the south. So we'll say VB final equals 10 root 2 comma negative 10 root 2 meters per second. So that gives us the final velocity of object B as a vector in terms of its xy components, as opposed to magnitude and direction. And why would we want that? What are we trying to figure out here? Or how could we figure that out? If our ultimate goal here is to figure out the final velocity of object A, what would be some useful physics principles to apply here, or some useful mathematical models?
Conservation of momentum.
Yeah, we know that momentum is going to be conserved here because how do we know that? Why would we expect conservation of momentum during this process?
There's no outside forces acting on the object.
Right. This object is exploding, so we can think of that as the 3 pieces pushing against each other during the explosion, but presumably they're only interacting with each other. Maybe there are some other forces involved, but we can assume that this explosion takes place over such a short period of time that the forces of the explosion are the only ones strong enough to really matter. So let's say that momentum is being conserved. That means the total final momentum of the situation has to equal the initial total momentum. And I think a momentum chart can be a very useful way to organize that information. That if we're keeping track of object A and object B and object C, and also the total, and we also want to look into the initial momentum, the final momentum, and the change in momentum. So P initial, delta P, and P final. Then we can use a momentum chart to keep track of all that. And we might not need all the information from the momentum chart. We may just be able to fill in part of it and get the information we need. But it's often a good starting point, just as a framework to organize all the information you have and piece together what do you know and what are you trying to find out. Like in this case, we can start filling in what information do we know right off the bat, right at the start here. The 45 cosine 45 Vx 20 meters per second. That was from, based on this triangle, the fact that we have, let me draw this a little bigger. If we have the velocity itself, 20 meters per second, I mean, you think of that as the hypotenuse of the triangle. Since we're ultimately trying to split this into the x component and y component, and those form a right triangle, since the horizontal and vertical components, or I guess I should say the eastward component and the southward component are by definition perpendicular. So since that's a right triangle, we can set up cosine of 45 degrees, that is this angle, either one of the angles really. But let's say we're using this as our 45-degree angle. Cosine of an angle would be, in a right triangle, would be adjacent over hypotenuse. So we can say that within this triangle, cosine of this angle, 45 degrees, has to equal the adjacent side, which is the x component, divided by the hypotenuse, which is 20 meters per second. Solve that for Vx, and you've got that x component, 20 times cosine 45 degrees. And yeah, let's fill in the initial speeds, because we know that even though it starts off as one unified object, we want to treat that one unified object as the 3 pieces we know it's going to split into. Since we know this is eventually going to split into 3 pieces, let's treat this as already being those 3 pieces we know it's going to split into anyway. We've got object A, object B, and object C. even though it's one unified piece right now, the fact that it's going to split into three pieces means we should treat it as starting off as three pieces already. Because it doesn't really make sense in a momentum chart to change how many objects you're talking about. So, but at the beginning, since they're all stuck together, they're all moving at the same initial speed. I guess I should say initial velocity, because direction matters here. So we can write out the initial momentum of each one by multiplying the velocity by each mass. So we multiply 5 meters per second to the east times m, we get 5m. We multiply 5 meters per second to the east times 2m, we get 10m. We multiply 5 meters per second to the east times 5m, we get 25m. So those would be the magnitudes of the initial momentum of each object. We could even draw those as arrows. Make this a different color. If we want to draw those as arrows, how would those arrows look? What would be the same? What would be different?
Would they all be going to the right?
Yeah, or let's say to the east. Let's go ahead and use north, south, east, west for this. So just to emphasize that we're not talking about up and down in the sense of gravity. So north, south, east, west. Just to have a common structure for describing directions. So these would all be going to the east, momentum pointing to the east. But what would be different about them?
The magnitudes would increase as you go down the alphabet because of the greater masses.
Yeah, and we can use the idea of proportions here, that we are going from 5m to 10m. 10m is twice as much, so it should be twice as big of a vector. And 5m versus 25m, that's 5 times as much, so this should be 5 times as big. And these don't necessarily have to be exact here, but just providing a rough idea of how these sizes compare. And I should actually probably draw these smaller because I'm going to need to add all these together. If we add these up, what would you expect about the result?
One long horizontal arrow to the right.
Yeah. Yeah, the result is going to be a vector because you're adding 5m to the right, to the east, plus 10m to the east, plus 25m to the east. Yeah, that should be 40m to the east. So 8 times as big as the original. And we can also write these in terms of components. If this was a one-dimensional problem, I wouldn't worry about that so much, but the fact that we are going to be dealing with 2 dimensions by the end suggests we should write these as components. Since these are all purely to the east, that's just an x component. So we got 5m comma 0, 10m comma 0, 25m comma 0, and 40m comma 0. And I usually just write the components in just in parentheses at the corner of the box. There's not really a universal standard for that. It's just it's important to keep track of the components. So I would just write them somewhere in the box. So that's everything we know about the initial situation. What else do we know here? Is there anything else we can fill out based on given information?
You know that the velocity final for the components of 5m should be 0 for both.
Yeah, we figured out the velocity, or we were given the velocity of object, the final velocity of object B. We split that into components. How do we turn that into a momentum?
Multiply by the mass.
Yeah, multiply that by mass, which we know is 2m. So in terms of the components, how do you multiply a vector by a scalar if you have it in terms of components?
Multiply each component by the scalar?
Yeah, each one of those gets multiplied by the scalar. So 10 root 2 gets multiplied by 2m, negative 10 root 2 also gets multiplied by 2m. So for object B, that'll be 20m root 2, negative 20m root 2. So those will be the xy components of the final momentum. Let me make some more space here. There we go. And we can also write it in terms of magnitude, because if you look at this in terms of its magnitude, the magnitude of velocity was 20 meters per second. If you multiply that vector by 2m, what happens to it in terms of magnitude and direction? If you take any vector and multiply by a scalar, what happens to the magnitude and what happens to the direction?
The magnitude changes, but not the direction.
Right. It's still going to be to this directly to the southeast at that 45-degree angle. But yeah, the magnitude is going to change from 20 to 20 times 2m. In other words, 40m. So that means this vector is going to be 40m to the southeast directly, not just approximately southeast, but exactly to the southeast at the 45-degree angle. And that's not really necessary. The 40m here isn't really needed for the calculations we're going to do, but it's a good idea to have at least a rough idea of how big it is so you can draw it roughly to scale with the other values that we've already drawn it, the other arrows. Specifically, this should be the same size as the initial total momentum, just in a different direction. Are there any other final values we know already?
C is 0.
Yeah, we know C comes to a complete stop, so its momentum will be the 0 vector. That is a vector whose components are all zeros. And we would typically write that as a big 0 with an arrow over it. So the number 0 with a little arrow sign over it, a vector sign, to say this is not just the number 0, this is a vector whose magnitude is 0. And yeah, we also know this final total momentum, because what do we know about the change in total momentum here? Yeah, we know there's also 0 change in the total momentum. So the total change in momentum is also the 0 vector, which again, we would draw as a 0 with a little arrow over it. Or to put it another way, a vector whose components are 0, 0. And therefore, the final momentum total is going to be the same as the initial momentum total, that same 40m comma 0. No change. So yeah, we have object B is 40m, the total is also 40m. Would that mean there's nothing left for object A?
No, because they have to add up to the final.
Right. And 40m doesn't just add to 0 and something else to get 40m, because the momentum isn't just 40m, it's 40m with a direction. These are vectors, so that means direction matters. You can't just add them up as numbers. So we've got to have some vector plus 40m directly to the southeast has to add up to 40m to the east. So we've got an unknown here. We don't know the x and y components of the final momentum of object A, but we can find them because we know what these have to add up to. So looking at this one component at a time, we can figure out what those unknowns are. And we can do that by saying, if we take a look at the x and y components individually, if we look at just the x components, we've got an unknown plus 20m root 2 plus 0 equals 40m. And likewise, if we look at the y components alone, we've got question mark plus negative 20m root 2 plus 0 equals 0. And I should probably be labeling these with variables, not just question marks. Let's call this, since it's the final momentum of object A, P final A x and P final A, Y in terms of the components. So how would we solve for P final A X component? How could we isolate that last unknown here?
Subtract 20m root 2 from 40m.
Yeah. So we get 40m minus 20m root 2. That's the X component. And likewise for the Y component. How would we isolate that?
Would it be 0 minus negative 20m root 2?
Right. In other words, adding 20m root 2, because we're just subtracting a negative. So positive 20m root 2. So we now have the X component and Y component. And that should give us the vector. So we've got X component 40m minus 20m root 2, and Y component 20m root 2. So we've got the X and Y components. Let me make some more room again. And also, without even running the calculations, approximately what direction would you expect that vector to be?
Positive in both directions.
Yeah, we know it's going to be kind of northeastish, not exactly north to the northeast in the sense of 45 degrees, but kind of northeast-ish. And we can even see that from the geometry here. If we say we've got three things that add up to 40m to the east, we've got this vector plus something has to add up to this vector. I guess I should probably make this a little longer, because those should be the same length. So the only thing that would add up in this way would be this vector. We've got final momentum of object B plus final momentum of object A adds up to the total final momentum. So putting these back, there's the final momentum of object B, final momentum of object A, and final total momentum. Any questions on that so far?
Wait, sorry, how did you get the A vector direction?
Vector addition, that if we have, like, let's say we have some XY coordinate plane. And we've got some unknown vector plus vector P final B. So vector P final B plus some unknown vector, which we could attach head to tail, has to add up to this total. So we could think of this as, what do we have to add to B to get to the total? And what we'd have to add to get to the total would be this much. That takes you from where you are now at the end of vector B to the total value we want. So that thing we have to add to B to get to the total would be the vector value of A.
Okay, thank you.
Mm-hmm. So we now have the momentum vector in terms of XY components. But what we're actually trying to find is, how fast is object A going and in which direction? So now that we've got the momentum, how do we convert this to a velocity?
Divide by the mass.
Yeah, we can divide this by mass. And we don't have a number for the mass, but we have a symbol for it. Velocity final of A is going to be this vector divided by the mass of A. And we were calling the mass of A just capital M. If we were using like mass of B, it would be divided by 2m or whatever the mass is. But in this case, capital M represents the mass of A. When we divide by M, what happens to these components? Or how would you divide a vector by m if you know the components? What happens when you have a vector written in xy component form and you divide by a scalar? What do you do with that scalar divisor? Yeah, we divide each component by m. So the first component divided by m and the second component divided by n. Just the same as if we were multiplying by a scalar. Because dividing by m is the same as multiplying by 1 over m. So it behaves the same way. We're just multiplying each component by 1 over m. So first component, the m on both of those terms cancels out. We get 40 minus 20 root 2. Second component, we divide by m, we get 20 root 2. And we've been leaving out the units of measurement here, but what should these units be?
Meters per second.
Yeah, all the velocities originally were given in meters per second. We've been multiplying them by mass, so they get meters per second times whatever units the mass is measured in. But when we divide by mass, that goes back to meters per second because the mass units cancel out. So this whole thing is in meters per second. We now have the final velocity of object A in terms of components. If we wanted to figure out how fast is this actually going, what would we do? If we want to know the speed.
Oh, we'd have to use the Pythagorean theorem.
Yeah, Pythagorean theorem would work well here because we know the components. We have the final speed is presumably somewhere mostly north and a little bit east. We know its x component is 40 minus 20 root 2. And we know its y component is 20 root 2. So 40 minus 20 root 2 and 20 root 2. We can use a Pythagorean theorem there. Square this side, take the square root, and that'll give us a result. So square root of 40 minus 20 root 2 squared plus, and then 20 root 2 squared is just going to be 800. So I'm getting about 30.6. So that'll be the actual speed. Object A is traveling at a speed of 30.6 meters per second. And what about direction? How could we find the direction here, other than just saying it's kind of northeastish? If we want more precision than that, how would we find that angle?
The arctangent of the y component over the x component.
Mm-hmm. Yeah, that should work because tangent of the angle would be x component, the opposite over adjacent, so y component over x component. So take the inverse tangent of that, and that'll tell us the angle. So inverse tangent, make sure calculator is in degree mode if we want degrees. Inverse tangent of 20 root 2 divided by 40 minus 20 root 2. And I'm getting about 67.5 degrees. So at a direction of 67.5 degrees north of east is how I would describe the direction. Using V to find the angle. Yeah, the thing is the speed and the momentum, the velocity and the momentum are the same direction. If you've got the velocity vector and the momentum vector, they're the same direction. So you're going to get the same angle no matter which one of them you use. Because ultimately, what's the only difference between momentum vector and velocity vector? How do you convert from one to the other? Yeah, mass. We were doing this without the mass, the 20 root 2 and the 40 minus 20 root 2. Those are the x and y components of the velocity. But if we were to change that by putting in the times mass. If we filled in a times mass here, on each of those components, what would that do? Yeah, if each one of these is multiplied by mass, the masses are going to cancel out when you take the ratio anyway. The trigonometry here is all about proportions. It's all about the ratios of the sides. The ratios of the sides are going to be the same regardless of whether it's multiplied by mass or divided by mass or what. So a scalar multiplier does not change the angle, does not change the direction. It only changes the magnitude and the units of measurement as well in this case. So you could, if you're looking for the angle, the direction of the final motion of object A, you could use the components of momentum or the components of velocity. They're going to be the same ratio. So that tells us the speed and direction of travel of object A. It's going to be traveling at a very steep north-northeast sort of angle and significantly faster than the other object involved. Any other questions on that? All right, and while we're at it, let's also get a quick start on, well, actually, before we do, if we did fill in the rest of this chart, if you filled in the delta momentum by subtracting final minus initial for each one, what information could you get from that central column? What would the delta P give you information about? What has to happen to cause a change in momentum? Yeah, the impulse on the individual objects from the other objects. In other words, force times time. So if you calculate the change in momentum of each of these by subtracting final vector minus initial vector, that will tell you the impulse each object is experiencing. For instance, object C is experiencing an impulse of 25 m to the west. That's because it's experiencing a westward force from the other objects. Presumably it's experiencing forces from object A and object B individually, but the total of those impulses is 25 m to the west. So the delta P tells you the total impulse each object is experiencing. How would you convert that to force? How does impulse relate to force?
Divide by time.
Yeah, impulse is force times time. So if you take that change in momentum, the impulse, and divide by time, then you get force. And the time here, the delta T, would be specifically the amount of time the explosion takes. So this is usually easiest to find if you have a slow motion video of the event. If you're watching this go in slow motion and you can actually time like how many frames of video it takes for the explosion to happen and convert that to time in seconds, presumably some tiny fraction of a second, then you can divide the change in momentum by the amount of time the explosion takes, and that tells you the average force each object is experiencing. And that will also be a vector because direction matters. Any other questions on this explosion problem? All right, then let's take a quick look at the teacup thing also. Can you see this all right? This one also involves an object that starts off as one object, but then shatters into, in this case, three objects, a 60-gram piece, a 100-gram piece, and a 200-gram piece. The main difference in this one, first of all, we know all three of the masses of the pieces, so we don't have to worry about writing those as variables. But we don't know how much time this takes. We know that the objects are moving in some direction. We know how far they travel. It tells us, for instance, after a short time, the 60-gram piece is 1 meter due east from the point of impact. Let's focus on that piece of information for the moment. If we know that the 60-gram piece travels 1 meter due east from the point of impact, that's a distance, but we know it takes a short time. What other information can you get from combining distance and time?
Velocity?
Yeah, we can think of this as velocity. The 1 meter due east is a displacement vector. It's a distance in a certain direction. So we can say that the 60-gram piece travels 1 meter. We can say, usually we call this r. The displacement vector is 1 meter to the east. So that's the displacement vector for the 60-gram piece. But to convert that into into velocity, we would divide that by time. So if you take a 1 meter vector and divide by a very short time, that changes the magnitude. The magnitude would now be 1 meter divided by that amount of time. But what would you say about the direction of the velocity? If you take a vector pointing to the east and divide by a scalar, what do you know about the direction of the result? Yeah, same direction. So the velocity of this object is going to be 1 meter divided by delta t. And then how would you convert that to momentum? Right, multiply that by the mass, which in this case is 60 grams. And usually we would convert the masses to kilograms, but in this case, everything's in grams, and it doesn't really have to interact with any other measurements. So I would just leave these in grams. So that means the momentum, the final momentum of the 60-gram piece is 60 grams times 1 meter divided by delta t, or you could just say, leaving out the units for now, 60 over delta t. So we can describe all of these momenta, even though we don't know how much time it takes, we can describe all the final momenta as something over delta t and a direction. And then you could even split that up into components. For instance, this one you could say is P final is, since it's to the east, 60 over delta t, comma 0. Or sometimes even easier, since you can factor out the delta t and 60, say 60, 0 divided by delta t. You could put the scalar outside of the vector, or outside of the components, with the implication that each component is divided by delta t. So 60 over delta t is the x component, 0 over delta t, or 0 is the y component. So you can use that idea to write out all of the final momentum components. And note that this chart splits it into 3 charts. You've got one chart for vertical, and by vertical we truly mean up and down, not just north and south, which is sometimes shown as up and down on a chart. When it says vertical here, it actually means up and down in the sense that this is a falling object. Then it hits the floor and scatters in north-south directions and east-west directions. So north-south and east-west are both referring to horizontal motion on the floor. It's just that the floor itself is 2-dimensional. So it's got a north-south component and an east-west component. So for instance, the 60, that's the eastward component of the 60-gram piece. So we could fill that in here, 60 over delta t. And then you could fill in the others. For instance, the 100-gram piece is moving 0.8 meters to the north. So what's the east-west component of its momentum? How much is the 100-gram piece moving in the east-west direction?
0.8 meters.
It's moving 0.8 meters to the north. How far is it moving east or west?
0?
Right, so we'd fill in a 0 here. And then the 200-gram piece, we don't know yet. Whereas for the north-south chart, we know the 60-gram piece isn't moving north or south at all. But the 100-gram piece, we know moves 0.8 meters north in some unknown amount of time, delta t. So we'd multiply once again in the same way, mass times distance over time. 100 grams times 0.8 meters of distance would be 80 gram meters divided by some unknown amount of time. So this would be 80 over delta t as the northward component of the 100-gram piece's final momentum. And likewise, the 200-gram piece, we don't know. At the very beginning, though, before the impact with the floor, do we know anything about the initial momentum of the whole cup? Which direction is the cup moving before it hits the ground?
Straight down.
So if it's moving straight down, how much of that is north, south, or east, west?
None.
Yeah, none of it at all. Moving straight down means it's not moving north or south, it's not moving east or west, it's just moving straight down. No north, south, no east, west. So at the beginning, all of the north-south components would be 0. And all of the east-west components would be 0. Whereas in the vertical direction, it starts off having a lot of vertical motion, specifically in the downwards direction. It doesn't really tell us anything about how fast it's moving when it hits the floor, but we at least know that all three of these are going to be downwards. They're all traveling at the same speed, so their momenta will be proportional to their masses. And at the end, everything hits the ground and scatters horizontally. At the end, there's no more vertical motion, so we know the final vertical components are all 0. I think that should be a good start. See if you can use that information to fill in all the rest of the momentum chart, because I think that's enough information to fill in the rest. Just be careful about which values you know are changing, which values you know are not changing. So try filling out the rest of that. Let me know if you have any other questions, and I will see you next time.